Welcome to NFPA 285, what it is, what it isn't, why it matters, and when it's applicable. NFPA 285 is an important yet often confusing or misunderstood topic. As an SAF sales rep who may encounter NFPA 285 when consulting with customers, this course will help you provide consultation with confidence. At the conclusion of this course, you will take a short quiz to ensure that you've retained the content presented in this course. NFPA 285. First, what's what and who's who. Let's start with what NFPA 285 is. In short, it's a fire test. Its purpose is to determine how an exterior wall assembly reacts in a fire event. The words wall assembly are key here. NFPA 285 is a fire test of an entire wall assembly, just as it will be constructed on a building. It's not a fire test for a specific building material, such as a wall cladding. The second important aspect of NFPA 285 is that it's directed at only certain kinds of wall assemblies, those assemblies that contain combustible materials. What makes NFPA 285 unique among other construction industry fire tests is its size. NFPA 285 is a full-scale test, 2 building stories in height. This illustration depicts the NFPA 285 testing apparatus. The 2-story structure's floors, ceiling, and back wall are made from concrete. Then a wall assembly to be tested is constructed in front of the structure, just as it would be on an actual building. A burner is located on the interior of the first floor, and an exterior burner is located on the exterior of the wall positioned at an opening or window in the wall assembly. As a full-scale test, NFPA 285 is designed to accurately predict how a wall assembly will perform in an actual fire event. Knowing this is critical because a wall assembly's ability to resist fire will determine whether or not there will be enough time for building occupants to safely exit the building. The total duration of the test is 30 minutes, and there are no grades. With NFPA 285, a wall assembly either passes or fails. The test is required by code only in certain circumstances. It's an expensive test, costing $50,000 to $60,000 per test on average. And it can be time-consuming. There are only a handful of testing facilities in North America. Between scheduling, prepping and shipping materials, building the assembly to be tested, performing the test, and analyzing the results, it can take 3 to 6 months from start to completion. That's an overview of NFPA 285. Now let's look at NFPA, the organization that developed the test standard. NFPA, the National Fire Protection Association, is a global nonprofit organization that was established in 1896. The NFPA is devoted to eliminating death, injury, property, and economic loss due to fire, electrical, and related hazards. Throughout its history, the NFPA has developed more than 300 codes and standards, all related to fire safety. NFPA 285 is just one of these standards. However, a test such as NFPA 285 is simply a test. That is, until the test is adopted as a requirement of a building code. The most widely adopted and influential building code is the IBC, the International Building Code. The IBC is developed and administered by the ICC, the International Code Council, and the IBC is, in fact, just one of 15 separate building safety codes, or I-codes, that are developed and administered by the ICC. The IBC, the International Building Code, is widely adopted worldwide. Here in the U.S., a combination of states, cities, or local municipalities are responsible for adopting and enforcing codes. Currently, the IBC is in use either partially or in total in all 50 states, including D.C. and U.S. territories. NFPA 285 is referenced in IBC Section 1403.5 and Section 2603.5.5. It's important to know that codes like the IBC evolve over time, especially as building and material sciences advance. IBC is updated and published on a 3-year cycle, with its next edition due in 2021. Let's review what we've learned so far. NFPA 285 is a test of an exterior wall assembly that uses combustible material. The National Fire Protection Association, or NFPA, develops the NFPA 285 test standard. The International Code Council, the ICC, develops building safety codes. The ICC's International Building Code, the IBC, is widely adopted and enforced worldwide. And NFPA 285 is referenced in the IBC. To understand when NFPA 285 testing applies, we first need to understand IBC Construction Types, IBC Occupancy Classifications, and building heights that are allowable according to construction type and occupancy classification. The IBC identifies 5 different construction types, 1 to 5, on a scale of increasing combustibility potential, where Type 1 is non-combustible construction and Type 5 is combustible construction. Type 1 construction buildings have the highest fire resistance rating and are made from non-combustible materials such as concrete, steel, and glass. Skyscrapers are typical of Type 1 construction. Type 2 is slightly less fire resistant because it permits more combustible interior materials and finishes. Type 3, less fire resistant than Type 2, allows for floors, roofs, and the structural framework to be built with any material. However, exterior walls must be constructed of non-combustible material. Type 4 also must have non-combustible exterior walls. However, the structure of the building, its columns and beams, can be constructed of large dimension wood, large and thick enough to provide a fire resistance rating. Finally, Type 5 construction can have combustible exterior walls and framing and is the least fire resistant. Single-family homes are often Type 5 construction. The IBC subdivides each construction type further as A and B. For example, within Type 2, there is Type 2A and Type 2B, where Type 2A is more fire resistant than Type 2B. Beyond the fact that there are many ways to construct buildings, the IBC classifies construction types in order to maximize the ability to save lives in a fire event. According to the IBC, the required construction type of a structure is dependent upon 3 factors. The first factor is what the intended end use of the building will be, referred to by the IBC as occupancy classification. Will the building be an office, a hotel, a single-family home, or a petrochemical production facility? The second factor is the height of the building from grade. And the third criteria is the type of fire sprinkler system that will be installed in the building. The IBC identifies 10 different occupancy classifications for buildings. You can imagine the differences in numbers of people and activities that occur inside a building based upon each of these classifications. Classification A for assembly is where people gather for sporting events, concerts, or movies. E is for education and is for classrooms with teachers and students and administrative offices. Whereas H for high hazard is where there are dangerous activities taking place inside with dangerous materials. Like with construction types, the IBC subdivides most occupancy classifications further to describe differences in each category. For example, A1 is for viewing performing arts and motion pictures. A2 is restaurants and bars, while A3 is for worship, recreation, and amusement. Construction type and occupancy classification come together in the IBC in this chart that defines the allowable building height in feet above grade plane according to occupancy classification, listed in the first column, sprinkler system, which is detailed in the next column titled See Footnotes, and lastly, construction type in the remaining columns. With construction type 1A, the most fire-resistant form of construction, buildings are permitted to be an unlimited height, shown as UL. Whereas a residential occupancy classification of Type 5B construction is permitted to be 40 feet in height or 60 feet with an automatic sprinkler system installed throughout. Note that every occupancy classification within construction types 1 through 4 allows for buildings to be constructed higher than 40 feet above grade. As we'll explore in a moment, this is a height where NFPA 285 comes into play in many instances. Let's review what we just learned. IBC construction types are based upon fire resistance, with Type 1 construction being the most fire-resistant construction and Type 5 being the least fire-resistant. IBC occupancy classifications are based on the intended end use of a building. A combination of construction type and occupancy classification determine the allowable height of a building per the IBC. These IBC codes are in place to preserve life in a fire event. Next, we'll look at the origins and the evolution of NFPA 285. Why do we have NFPA 285 today? The culprit is plastic. However, it would be wrong to assign blame to plastics based upon nefarious motives. In the 1970s, the U.S. found itself in an energy crisis. Consequently, the construction industry sought ways to make buildings more energy efficient, and rigid foam plastics were a viable solution. So it wasn't long before these combustible materials were being installed on walls that were supposed to be made of non-combustible materials. Tragically, fires and deaths occurred that were attributed to this practice, which in turn led to a 14-month investigation by the U.S. Federal Trade Commission, alleging deceptive marketing on the part of the plastics industry. Specifically, that the plastics industry overstated the fire resistance of its products. In 1974, a consent decree was reached that required the Society of Plastics Industries, or SPI, to pay $5 million for the research and development of reliable flammability testing techniques. SPI developed this test, and in 1976, a fire test for foam plastic insulation is first referenced in the Uniform Building Code, the predecessor code of the IBC. This timeline details the evolution of today's NFPA 285 test. By the late 1970s, SPI had completed the terms of its consent decree. The tests they developed to determine the effects of foam plastic insulation in a wall assembly would be full-scale, a full 2 stories in height. Over the next decade, the test would be refined numerous times, and by 1988, the test is officially adopted by the Uniform Building Code as UBC 17-6. The test would evolve further to become UBC 26-9 in 1997. Just 1 year later, NFPA decides to adopt the very same test as part of its body of fire test standards, and they rename the test NFPA 285. In 2000, the Uniform Building Code is replaced by the IBC, and NFPA 285 becomes part of the IBC. Remember, originally, NFPA 285 was only concerned with plastic foam insulation. However, throughout the 2000s, IBC expanded the requirements for NFPA 285 to include wall assemblies made with exterior insulation finishing systems, or EIFS, aluminum composite material, or ACM, and fiberglass reinforced panels, or FRP. And in 2012, IBC added high-pressure laminate, or HPL cladding to its list, then went a step further by including combustible weather-resistant barriers such as Tyvek building wrap. Later, in 2015 and again in 2018, the IBC added exceptions for certain weather-resistant barriers based on their specific material properties and fuel load potentials. As new products using new materials in new ways come to market, it's reasonable to expect that the IBC will continue to evolve requirements for NFPA 285 testing accordingly. To summarize, today there are 3 different categories of materials that, if used in a wall assembly, may trigger NFPA 285 testing. First is plastic foam insulation, or any combustible insulation. Second are combustible weather-resistant barriers, with exceptions. And third are combustible claddings that include EIFS, MCM, ACM, FRP, and HPL. Since the common characteristic of all of these triggers is whether or not a material is combustible, let's look at NFPA's definitions for combustible materials and non-combustible materials. Section 3.3.2 of NFPA 2019 provides a straightforward definition for a combustible material. It's a material that, in the form in which it is used and under the conditions anticipated, will ignite and burn, a material that does not meet the definition of non-combustible or limited combustible. For non-combustible materials, Section 4.1 of NFPA 2019 provides this new entry. To be considered non-combustible, a material must comply with at least one of 3 possible conditions as follows. The first condition is straightforward, that the material in the form in which it is used and under the conditions anticipated will not ignite, burn, support combustion, or release flammable vapors when subjected to fire or heat. Solid metal or masonry are good examples here. A second possibility concerns an industry test standard that the material is reported as passing ASTM E136 standard test method for behavior of materials in a vertical tube furnace at 750 degrees Celsius. And the third, like the second, also relies on an industry test standard that the material is reported as complying with the pass-fail criteria of ASTM E136 when tested in accordance with the test method and procedure in ASTM E2652, standard method for behavior of materials in a tube furnace with a cone-shaped airflow stabilizer at 750 degrees Celsius. Let's review. NFPA 285 traces its history to the use of plastic foam insulation in exterior walls beginning in the 1970s. NFPA 285 has evolved over time and has been adopted by the IBC. In the past 20 years, the IBC has added NFPA 285 testing requirements for wall assemblies containing combustible claddings and combustible weather-resistant barriers. NFPA 285 provides formal definitions for determining combustible and non-combustible materials. Now let's take a deeper dive into the test itself. Earlier, we showed you an illustration of the test apparatus. Here are schematic views, both front and side. The front of the apparatus structure is open to allow the wall assembly to be constructed in front of it. The total height of the structure is 16 feet 10 inches, but the wall assembly, when built, will extend beyond the top of the structure. Note the location of the required opening in the wall assembly to replicate a window, as well as the placement of the interior burner and the window burner. When the wall assembly is built and attached to the front of the structure, an array of thermocouples are installed in prescribed locations throughout the assembly. 80 of these thermocouples will be monitored and recorded for temperature during the test, and 48 of these thermocouples will be used in determining whether the test specimen passes or fails. The required width of the window opening is 78 inches. And for panelized cladding, such as ACM, the test requires that there be continuous vertical and horizontal joints included in the assembly. At least one vertical joint must extend from the top of the window to the top of the wall within plus or minus 12 inches of the window's center line. And at least one horizontal joint must be included that is continuous across the entire width of the wall and positioned between 1 and 3 feet above the top of the window. Tested wall assemblies may have more panel joints, but these are the minimum requirements. For cladding systems like eaves that don't have joints, this requirement is not applicable. Once all the test equipment is carefully calibrated, all thermocouples are measuring correctly, gas flow rates are correct, the test can begin. First, the burner in the interior room is ignited. Then, at precisely 5 minutes, the window burner that has been pre-ignited is wheeled into position directly under the window opening. Then, for the next 30 minutes, both burners continue to burn with the intensity of the flames increasing every 5 minutes. During this time, temperature measurements are recorded from the thermocouples, and a series of visual observations are made and documented with video and/or still photography. As mentioned earlier, NFPA 285 is a pass-fail test. There are 3 parameters that must be met in order to pass NFPA 285. If any one of these 3 parameters are not met, the wall assembly fails the test. First, there can be no flame propagation to the second story of the test structure. Secondly, flames may not reach vertically 10 feet above the top of the window opening or laterally 5 feet in either direction of the window's center line. Third, the thermocouples must not register temperatures that exceed maximum allowable temperatures. If an assembly achieves all 3, the assembly passes NFPA 285. There's a common misconception in the industry about NFPA 285 as it relates to building components and materials. This misconception is that a component or material can be NFPA 285 compliant, As you've learned, NFPA 285 is a pass-fail test for a wall assembly, not a specific component or material. Therefore, only a wall assembly, the sum of all components and materials in a wall assembly and in a specific configuration, can be NFPA 285 compliant, and that is if this assembly passes NFPA 285. Of course, there are numerous other fire tests designed for individual building materials. These tests form the basis of a fire rating for an individual product. We've all heard of products that have a Class A fire rating, for example. This fire rating is determined based upon material level tests, such as ASTM E84. So be on the lookout for manufacturers who make claims that their products are NFPA 285 compliant. The manufacturer of the extrusion shown here markets this extrusion as NFPA compliant. As you've learned, this simply cannot be true. To review, NFPA 285 is a full-scale two-story fire test. The wall assembly is continuously exposed to fire for 30 minutes. An assembly either passes or fails the test. For panelized cladding such as ACM, the test requires at least one vertical and one horizontal joint in precise locations. During the test, visual observations and temperature measurements are made, and only wall assemblies can be NFPA 285 compliant, not specific components or materials. The IBC mandates NFPA 285 testing in specific instances, so let's look at when the test is required. This flowchart helps a building team and code officials to determine if NFPA 285 testing is required for a particular wall assembly and building design. You begin on the far left. The first question in the dark blue rectangle is whether or not the building is construction type 1, 2, 3, or 4. If the answer is no, your path flows downward and to the right to the green circle, where NFPA 285 compliance is not required, which means NFPA 285 testing is not required. However, if you answer yes, your path flows upward and to the right to the first light blue rectangle, where you have to answer a second question. Is foam, plastic, or combustible insulation used in the wall assembly? If your answer is yes, your path continues to the right, and NFPA 285 compliance testing of the wall assembly is required. But if you answer no to the foam, plastic, or combustible insulation question, that is, there is no foam, plastic, or combustible insulation in the wall assembly, you flow downward to the middle light blue rectangle to answer the next question, which is the cladding combustible, and is the cladding installed greater than 40 feet above grade? Note, there are two parts to this question. First is whether or not combustible cladding is used. Remember, EIFS, MCM, ACM, FRP, and HPL are combustible claddings. Here you might answer yes. However, note that there's a second part of the question. And is this cladding installed greater than 40 feet above grade? Although you may have answered yes for the first part of the question, for the second part of the question, you might answer no because, in the case of your design, the combustible cladding will not be installed greater than 40 feet above grade. Therefore, only if you can answer yes to both parts of the question do you flow to the right, requiring NFPA 285 testing. However, even if you answer yes to the first part of the question, that there is combustible cladding, if you answer no to the second part, that the cladding is not installed greater than 40 feet above grade, then you continue to flow downward to the bottom light blue rectangle to answer the next question. Like the previous question, this question has two parts, but relates to the weather-resistant barrier, or WRB. If you answer yes to both parts of this question, then you flow to the right, where NFPA 285 testing and compliance is required. But if you answer no, taking into account both parts of the question, then you flow down and to the right to the green circle, and NFPA 285 compliance is not required. Another common misconception about NFPA 285 is the ability to make changes to a tested assembly and remain compliant. While there may be no appreciable material difference in a certain brand of insulation or cladding material or extrusion over another, the test strictly prohibits substitution. Additionally, the test prohibits rearranging the position of materials within an assembly. Any change in material, which includes the use of a different brand of what is essentially the same material, or the change in the position of a material within an assembly, requires retesting. Let's recap key points of what we just learned. NFPA 285 applies to construction types 1, 2, 3, and 4. If foam plastic insulation is included in a wall assembly, NFPA 285 testing and compliance is required. Wall assemblies that do not contain plastic foam insulation are potentially subject to NFPA 285 testing if they will be installed greater than 40 feet above grade. And if anything in an NFPA 285 compliant assembly changes, then retesting of that assembly is required. Up to this point in the course, we've examined NFPA 285 based upon the requirements of the International Building Code, or IBC. As you've learned, these requirements are strict. However, in the U.S., in the real world of construction, the reality of how NFPA 285 compliance is met is often different. Let's look at the important role engineering judgment plays in NFPA 285 compliance. As you can imagine, NFPA 285 compliance presents serious challenges to the AEC industry. Architects often complain that it restricts their design choices. They are either put in a situation of designing a wall assembly that will require NFPA 285 testing, adding to project costs and delaying schedules, or forced into selecting an assembly that has already been tested as NFPA 285 compliant. Another issue relates to NFPA 285 causing us to sacrifice building materials that can significantly help buildings be far more energy efficient and water resistant, key performance criteria in our quest to make buildings more sustainable and healthier. For building materials manufacturers, NFPA 285 has added significant cost as well. If a manufacturer wants to be specified, architects are requesting that the manufacturer assist them in prescribing the entire wall assembly, including those materials they do not manufacture, and to pay for the NFPA 285 testing. Large manufacturers with deep pockets generally welcome this as a way to edge out their smaller competitors. Unfortunately, this in turn reduces competition, disincentivizes innovation, and drives up cost. From a purely practical standpoint, traditional design, bid, build contracting becomes problematic since brand substitution is prohibited, which again reduces competition and drives up costs. And again, the test itself adds significant costs to a project and can delay schedules, making fast-track construction an impossibility with untested assemblies. The good news is that the industry, comprised of many pragmatists, knows how to solve for these issues while maintaining the high safety standards of NFPA 285 and the IBC. Returning to our NFPA 285 testing determination flowchart, there is a popular alternative, a workaround, if you will, that architects and contractors turn to in lieu of NFPA 285 testing of a wall assembly. This alternative is an engineering judgment that is based upon the performance of one or more wall assemblies that have previously passed NFPA 285. An NFPA 285 engineering judgment, also known as an engineering evaluation, is a detailed analysis of a proposed wall assembly by an expert who is intimately familiar with the NFPA 285 test. This expert renders a professional judgment as to whether or not the proposed wall assembly would pass NFPA 285 testing if it were to be formally tested. The expert bases his or her decision on a variety of factors and relies heavily on the performance of tested NFPA 285 compliant assemblies in making a determination. It's important to point out that the International Building Code, or IBC, is a code, not an enforcement authority. The entity that enforces building codes is the Authority Having Jurisdiction, or AHJ. Who the AHJ is depends upon where a building is being constructed, and it's the responsibility of this AHJ to enforce the codes that apply within this jurisdiction. In the U.S., it's not uncommon for engineering judgments to be presented to and accepted by AHJs in order to demonstrate compliance with a particular building code. So, depending upon the AHJ, an NFPA 285 engineering judgment may be accepted in lieu of NFPA 285 testing compliance, so long as the EJ is well-founded and from a well-respected industry expert. SAF-Commissioned an engineering judgment from one such industry expert, Priest & Associates Consulting, LLC. This evaluation was completed on June 26, 2020, and renders a judgment for the use of 6 different SAF extrusions for use in a wide variety of wall assemblies. These assemblies include both ACM, MCM, and all aluminum cladding. It prescribes the brands and specific product names of ACM, MCM that are permissible, as well as all other wall assembly components, brands, and product names for sheathing, WRBs, and insulation. SAF's EJ clearly makes the case that SAF extrusions in place of other brands of extrusions will not alter the results of NFPA 285 tested and compliant assemblies where these other brands were used. In short, this document arms SAF with an NFPA 285 engineering judgment for the use of SAF extrusions in a myriad of combinations of wall assemblies utilizing ACM, MCM, or all aluminum panels, a kind of a la carte or build-a-wall approach. For projects where an AHJ will accept an NFPA 285 engineering judgment, this document should be provided when SAF extrusions are used, but where the assembly in which they're used hasn't been NFPA 285 tested or won't be tested as part of the project. This is particularly useful for fabricators who wish to substitute other extrusions for SAF extrusions. Of course, there are some AHJs that may not accept an engineering judgment. Also, there are some architects who resist or refuse to use engineering judgments. That's why SAF has also commissioned its own NFPA 285 testing. SAF commissioned NFPA 285 testing using the SAF C4000 ACM rain screen system in a wall assembly. The test was performed at NTA Fire Lab in Bryan, Texas in May of 2021. As anticipated, the wall assembly passed the test. A total of 21 SAF C4000 wall panels made from 4mm Allowable plus ACM were used in the wall assembly. The design of the wall went above and beyond the minimum test requirement by including 3 continuous vertical joints above the window and 3 continuous horizontal joints above the window. Remember, only 1 continuous vertical and 1 continuous horizontal joint is required. In addition to SAF C4000 wall panels, the balance of the wall assembly included 2-inch thick 4PCF mineral wool exterior insulation, Tremco Exo Air 230 weather-resistive barrier, 1/2-inch Georgia Pacific dense glass exterior sheathing, and aluminum Z-girts. Passing this NFPA 285 test is important for SAF because now SAF can prescribe 2 complete wall systems that are NFPA 285 compliant. Passing the test reinforces SAF's existing NFPA 285 engineering judgment. Also, the tests may serve as data to justify future engineering judgments where SAF extrusions are used. This concludes the course. You will now take a 10-question quiz.